Hello, Algebra 1. This is Mr. Morales, and today we are going to be beginning our last topic for Algebra 1, which is exponential functions. These notes are going to be different because I'm sending you guys a PDF copy, so you can either write everything down by hand, or you can print out the PDF and write it down, by hand as I write it, or you can use an application like Kami to go ahead and upload it and digitally fill in everything. Either way, you'll either have to send me a copy of this PDF with the notes filled in, or you will send me an image of your completed notes and everything written down, all the examples done in the same style that I do them. All right, so let's go ahead and begin now. Exponential functions. First of all, there's a base formula, a parent formula, if you will, for exponential functions. Let me move this up a bit. And the function or the equation is y equals some number we call a times another number we call b. And what makes these equations special is that everything's going to be raised to the x power. So now you have an exponent of x, hence the term exponential functions, because all these have an exponent of x. Now, exponential functions in our first line are defined by the equation of the form y equals a times b to the x power. Sometimes a will be a number bigger than 1, sometimes it won't be there at all, and you'll just have b to the x. So either form you might see it in. This is the most popular form where you have some number to the x, but sometimes there's a number in front that we call a. All right. Now, there's a couple of things that are going to happen. First of all, if the number that has the exponent x is bigger than 1 or greater than 1, the function is what we call an example of exponential growth. And it's like a T. Finally got my board fixed, so I'm able to make new and fresher videos. All right, exponential growth. And that's what we call an increasing graph. And you will see this in our examples below as you do them. So go ahead and just write it down for now. You don't totally understand what I'm saying yet. And if the b number that's attached to the x with the x exponent is something smaller than 1, like a fraction, then when we have what's called exponential decay, it's a little too hard. And the opposite of growth, what we have is decreasing function. And once again, this will become obvious with our examples. So go ahead and write that down. Now there's a new word you guys need to learn for today, and that's going to be the word asymptote. And it is it's a line which a graph, or I guess a graph, gets close to but never crosses. Graph gets close to, I would say, but never touches or crosses. So basically, it's like an invisible border. Never, oops, let me erase that really quick. Hold on. Never touches or crosses. So it's kind of like a fence that your graph will get really, really close to, but will never ever pass. And you're going to see it in the example of these graphs that we're going to get to right now. So let me go ahead and move my paper on up. Where's my cursor? There it is. So I can get it to move up. There we go. So here we go. First example. Classify as an exponential growth or decay. Create a table of values and graph. Then identify its key characteristics. So here's how we're going to find the points of this graph. They first give us the equation y equals 2 to the x. We need to make a list of points. So what I'm going to do is I'm going to make an old school table. This first table I'm going to make is going to have 3 columns. The rest will have 2 when you see how I manipulate it. You always want to have some negative numbers you're going to plug in. You always want to have 0 and at least 2 positives. These are the most popular numbers to use when you're making your own graph of a table. Whoops, didn't mean to shake it there. My hand gets in the way there. Sorry about that. All right, so let's go ahead and see what this table means. So our equation is 2 to the x power. So if you're using a calculator, you're going to put 2 to the negative 2 power, 2 to the negative 1 power, 2 to the 0 power, 2 to the first power, and 2 to the second power. Now from the bottom up, you know these answers. 2 squared is 4. 2 to the first power is 2. 2 to the 0 power. So here's a big idea for this lesson. Anything, ever, any number to the 0 power is always going to be 1. Doesn't matter what number is in front of it, whatever is raised to a 0 power is always 1. Now we're going to have, here's a negative 1 right here, 2 to the negative first power, which ends up giving us 1/2 or 0.5. And then we have 2 to the negative 2, which is 1/4 or 0.25. So let's graph these points. I have negative 2, negative 0.25. So negative 2, and I go up just a quarter of a square about right here. Negative 1 is at 0.5, so it goes up about half a square right there. At 0, it's at 1, 0, 1. When x is 1, y is 2, so 1, 2 is my next point. And then 2, 4 is my next point. Now there are more points to this, but most of them won't fit. For example, if I plug in a 3, then I have 2 to the third power, which is 2 times 2 is 4, 4 times 2 is 8. Actually, that might fit. Let's see. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Right there. It does fit. And then the rest of the points will not fit. So if I was to connect my dots, here's the graph I would get. First of all, I have a line that gets really, really close to the x-axis, but it never touches. These numbers that came in front were all infinitely small, and if you use Desmos and look at the table, you'll see that all these numbers down here get really, really, really small and get really close to 0, but they never actually equal 0. And then as you go from left to right, these numbers start getting bigger and bigger and bigger, and then they shoot up exponentially, as we say. So that is what the basic exponential graph looks like. If you read the graph from left to right, it goes from small to big, so that means we have what's called growth. Now this graph for the domain, we want to know how far left it goes and how far to the right. Well, because it has arrow tips, it's going infinitely to the left, and then this curve actually curves up and keeps going to the right. Even though it's at a slight angle, it does keep going to the right forever. So because it does that, we have a domain of all real numbers. That means it goes forever left and right. All real numbers. I'll just abbreviate it with the number sign. All right, now the range. The range is the height of the graph, and that has a specific value. This graph does not ever, and I'll kind of draw the line there. Let me change the color really quick. So the graph gets really close to the x-axis right here, but it never actually touches. If you check your table, this y never actually equals 0 no matter how far up you go. It'll get really close to 0, but it'll never equal 0. So the range for all y values is every single number greater than, but not equal to 0. So everything bigger than 0 is your range. The y-intercept is wherever the graph touches the y-axis, and that's at this point right there. So that would be at 0, 1. The y-intercept shall always have a coordinate of 0 in the x, and then some number over here, in this case 1. And then now it wants to know what the asymptote is. What is the invisible boundary that it gets really close to? Well, we have a horizontal or a left-right border, and in this case it's the x-axis. The x-axis is represented as this line right here that crosses y at the value of 0. That's our asymptote. That's our imaginary border that this blue graph gets really close to. And you can verify all this with Desmos and explore the table more if you want to see the values. But that's the basics of the first example. Excuse me. Let's go ahead and go now to the second example. So I can move this up a little bit. Let me get rid of my pen. Here we go. Second example. Now, look at this first example. We had 2 to the x power. Now we're going to have 1/4, a fraction, a number smaller than 1 to the x power. So let's go ahead and figure out how this is going to look. I'm going to begin by creating a table. Now, I might keep it 3 columns just to show you how you get the values. Basically, I'm going to have the fraction 1/4, and whatever number I have in this row or this column, for x, is what I'm going to plug into the equation. So for example, I'll start with -2, -1, 0, 1, and 2 again. Oops, my graph keeps moving. So that means I have 1/4 to the -2 power, 1/4 to the -1 power, 0 to the, 1/4, let me erase that just to make it nice. Let's not be lazy. Erase that really quick. So I have 1/4 to the 0 power, 1/4 to the first power. Maybe I should put these in parentheses so you can see it a little better. Oops. And then I have 1/4 in parentheses to the second power. So what do all these numbers equal? I'll give it to you in number form. So 1/4 to the -2 power, if you play that into decimals or your calculator, you're gonna get 16, and then you get a 4, then you get a 1. Look at our numbers are getting smaller and smaller. Then we get 0.25, and then we get 0.0625. So they start getting infinitely small, and actually they're getting really close to 0, but like in the example above, they will actually never touch 0. The only way an exponent ever equals 0 is if your numerator in the fraction is a 0, but we have a 1 on top, so we will never ever get to 0. We will just get infinitely close. So let's graph this to see what it looks like. We have -216. That's going to be left 2 up 16 squares, but I don't have enough squares, so that point gets left out. But I can fit this next point in, -1, 4. Back 1, up 1, 2, 3, 4. So here's my first point right here. 0, 1. So I don't go left or right. I just go up 1 square on the y-axis. I have 1 1/4. So I go over 1, and then I go up just 1/4 of a square, so just above the black line. 2 and 0.065. That's going to be graphically on the picture. It'll look like it's right on the line, but technically it's just barely floating above it. And the rest of the points just kind of get infinitely close going this way. So my graph would look something like this. It is a curve. I maybe shouldn't have gone so close. I really actually should not have gone over the x-axis. So let me erase this curve and make it a little better. So the graph should, oops, I hate that it moves the thing like that. Let's try this again one more time. So here's my line. Let's come down. And then let's stay above the x-axis. There we go. That's better. Now read this graph from left to right. It starts off really tall and then it goes down. So that's an example of decay. What's the domain of this graph? Well, the domain is the same as above. These graphs go forever left and right, so their domain is all real numbers. Another way you might see this is written in the form of -infinity. Oops, that's not an infinity symbol. That's an 8. That's an infinity symbol. If it'll come out, let's try this again. There we go. -infinity to +infinity. That's going to be more rare though in the answer choice. All real numbers will be the phrase you see most of the time. Now the range of this, what's the height of this graph? Well, this graph is everything above the x line. So we have another asymptote again. Let me go ahead and change the color on this. And the graph gets really close to this line right here, but never crosses it. So the range, which we'll call y, is everything above, but not touching 0, or this line right here, because this is 0 on the y-axis. Like this is 1 square above, this is 0, that's -1. So it gets really close to 0, but it's everything above it. It doesn't go below it, or even touch it. What's our y-intercept? Wherever the graph touches the y-axis, which is right here at this point, just like above, it's also again 0, 1. And then what is our asymptote? Well, also just like above, this same x-axis acts like our imaginary border. The graph doesn't ever cross, so it's at y equals 0. Because every point on this line has a y-coordinate of 0. That's why we write it like that. All right, so those are 2 examples. Let's go ahead and go on to the next one. Here, now we have a bit of a difference. We have 3x minus 1. So 3 to the x power, minus 1. So let's go ahead and figure out what that's going to look like. What you're going to do is make a table again. I might as well just keep it a 3-column table. So we'll set it up, which I expect to see on your notes. 3 to the x power minus 1. Let's pick at least 5 points. We always want -2, -1, 0, 1, and 2. You always have to have 0 because things happen at 0, and 0 is a really easy exponent to deal with. So then we're going to have 3 to the -2 power minus 1, 3 to the -1 power minus 1, 3 to the 0 power minus 1, that is a 0, 3 to the first power minus 1, and 3 squared minus 1. Start with the easy ones. 3 squared is 9, minus 1 is 8. 3 to the first power is 3, minus 1 is 2. 3 to the 0 power is 1, because remember, anything to the 0 power is always 1. 1 minus 1 is 0. 3 to the negative 1 power. 3 to the negative 1 power is going to give us a fraction of, I believe, 1/3. And 1/3 minus 1 gives us negative 0.6 repeating. And then 3 to the negative 2 power gives us negative 0.8 repeating. You can use your calculator to verify those if you'd like. All right, now let's go ahead and graph these points. So we go to -2 to negative 0.8. So that's going to actually be below. It's going to be -2 and negative 0.8 is almost one whole square below. -1, negative 0.6 is a little bit past the halfway mark, so it's a little bit higher. We have a point at 0, 0 right at the origin. 1, 2 is our next point, and then 2, 8. 1, 2, 3, 4, 5, 6, 7 is our final point that fits. So our graph would look something like this. Then shoot up, and then goes on infinitely in that direction and infinitely to the left. So let's go and talk about what we see here. Do we have growth or decay? If you read the graph from left to right, like you always should, it goes upwards, which is indication of growth. The domain is always the same for all these, all real numbers. The range always talks about y. Since this graph goes upwards from left to right, it's going to be greater than something. What is it greater than? Let's find out where its imaginary border is, and I'll just use a different color for that. Well, the graph lines up right here, this imaginary border. This value right here is at -1, so y is greater, or everything above, but not touching -1. What's our y-intercept? Wherever this purple graph touches the y-axis, that's right here at the origin, at 0, 0. And then the asymptote is this line right here, this dash one, where y equals this value of -1. All right, so let's go ahead and try number 4 now. Number 4, very similar. We'll begin it the exact same way. We're going to make a table first, 3-column table. This is old school algebra, where we have everything's going to be 1/3 to the x power plus 4. Here's our values we're going to plug in. These are the smallest numbers and the easiest ones to use, and that usually have values that fit. So 1/3, you write this in, parentheses, and then everything's going to be raised to the -2, -1, the 0, first, second power, plus 4. Here's the work you would actually do in your calculator, or the table function. When I get you guys the Inspire, I'll show you how to pull up a table really quick to get the values. And here's the points you're going to get. You're going to get a 13, a 7, a 5, a 4.3 repeating, and then a 4.1 repeating. So our numbers go from bigger to smaller, so we should be seeing a decreasing graph. Let's see how it looks. -2, 13. -2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Would be like right here if the grid was big enough. -1, 7 is back 1, up 7, 1, 2, 3, 4, 5, 6, 7. 0, 5, 0, 1, 2, 3, 4, 5 right here. 1, 4.3, go over 1, 1, 2, 3, 4, and a third of a square, so right here. And 2, 4.1, 1, 2, 3, 4, so you're just about. So we can already see that our graph comes down about right here, and then curves and gets infinitely close, which I'll scoot back up to this line right here. Here's what it looks like. From left to right, the graph is going downwards, which is a sign of decay. Our domain is always all real numbers. If you learn anything from this lesson, it's the domain is always all real numbers. The range, which always talks about y, has to do with the lowest or highest this graph goes. And it has to do with that invisible border that it always gets close to. In this case, our invisible border is right here. So where is that at? That's at, on the y-axis, it's at positive 1, 2, 3, 4. So our range is all the y values above, but not touching on the y-axis. What is our y-intercept? Wherever it does touch the y-axis. That's right here at 0, 1, 2, 3, 4, 5. And then our asymptote is this little dotted line I made. The asymptote is always a y-line, and it's where the y-line is equal to 1, 2, 3, positive 4. All right, so those are 4 examples. To complete your notes, I'm going to leave you guys to do number 5 and number 6 on your own. Use Desmos or whatever calculator you want to get your values. Make sure you show me a table, an XY table with 3 columns. So something like this, with all the numbers filled out, the appropriate formulas written down. I would use the same standard numbers, -2, -1, 0, 1, and 2, for all of them, just to make your life a lot easier. And then your y values over here, whatever you get, should all go right here. I should see a graph, either increasing or decreasing, and everything in this side filled out as well. So do that for number 5 and 6, and that'll count as your notes grade for this day. If there is any confusion or you have any questions, by all means, feel free to ask me and let me know. All right, so number 5 and number 6 are yours to do. There will be an assignment attached to this, so look out for that as well. Have a good day and best of luck.